and good afternoon to all of you.
With that time, what our research within interdisciplinary domain, for example, particularly in biology and ecology and collaborating with a lot of people, what we have understood that there are several domains where there's a heavy lack of data as well. So I just want to take this opportunity since it was not planned, but since it's a very diversified audience. So if you can see my screen, so this is actually one of the database that we have recently created. It's a national level data repository for invasive species, and in India particularly. And when we have thought of emphasizing on R particularly, that we every year actually every 2 years we used to arrange a workshop on species distribution modeling. It's a 7 days program for scientists and faculty members and research scholars and postdocs. So where we try to understand the geographic distributions of different species and try to model them under climate change, and would like to see that and whether there is some kind of policy formulation, policy change, these things also needed or not. So just before lockdown, when I thought of doing that analysis for India, because a lot of countries have taken that initiative, but unfortunately we are not able to find the data in a single place. So just before the lockdown, we have taken an initiative and thought of let us use this lockdown period to make a repository, data repository for this. So this is called as India Allial Flora Information Database. So we have given that name as an ILORA. So I would request you, all of you, to as much as possibly circulate this information about this database. And so it is a publicly available database. So all the analysis and everything, whatever we have done over here, many R script and Python script and many analysis has been done. So lots of codes, R codes, what we have used to extract information, analyze the data, these are also being made available in this over here. So if you see that these are some of the, you can access data, it's a publicly available data, right? So we have now version 1.1 actually also have come. So just recently it appeared in Ecology, the one of the top journal from Ecological Society of America, you know that. So we have covered this many data, this many information we had. Now we have more and more information in the version 1.1 has come. So why I'm showing it that a lot of people are because R we typically consider R as a kind of we will give some input data and we will get as an output. It has a remarkable capacity. So just to show on that, because every analysis on this has been done using R only. So if you see that if you want to get into this data and occurrence, then you'll be getting that this link will take you to this link, and you see that you can submit data also. We'll do the scrutiny, cross-checking, and everything, and we'll integrate that into our system. If you want to access the data, you can click over here, access the data. And this is another good application of R that we have done. So if you click on this, we have make a small web application also on this. Just it may take little while to load. So it will take you over there. So you can get access of the data from here, right? You can have little bit simple visualization also. You can select species that which one you want, and you can select on the map also. You can see that in what are the basically the occurrence records on the Indian map. You would be able to visualize these things. So we are working on more enhanced capabilities on this database. So again, everything is based on R. So if you want to know more about this, you can have our recent publications. More works are going on, and couple two PhD students are working on this. So this is the database paper. Then we have also proposed a policy, what kind of policy change probably needed for plant invasion control in India, and there are what are the drivers for invasion success in Indian context. and also the latest that one for version 1.1 has come up. So I would request you all to like have a look at this database. So I'm just putting it in the comment box, and share this information uh, to your colleagues, to your friends, and and wherever you are working. Okay. So with this, I think let me come back to our today's topic, which will be talking about the multivariate methods in R. So to start with that, so this is you all have, as I had a small discussion with Dr. Joshi, that you all are now comfortable with what is called as a R Markdown. So you all are comfortable, right? So as you see that, if you can see my screen, that there is a file, you can see that there is a lot of things are written. So with any multivariate statistics or a multivariate analysis, it always starts with a multivariate normal distribution. So if we all know about the normal distribution, it must have been covered. So as we know, there is a bell-shaped curve, and it has a some several desirable features. Mean, median, mode, everything is same, and also a high probability region is near to the mean itself, right? So as multivariate normal distribution, it extends to the higher dimension, and and this is the markdown file which I have created uh, for I updated for your particular audience. So if you observe it, so let me just, if you have done it already, that neat HTML. So let us see what it is coming. So it is rendering. Probably you have already seen it. Yes, it is rendering is happening. Yes, as you can see, there's some. Yes, it has come. Everybody can see this screen.
Yes, sir, it is. It is
Yes,
visible.
yes. So the idea is that why I did create it, because when we go for it, because in initial lectures you probably have written some simple functions and some of the important like visualizations, but here with multivariate normal, when it comes, it's a very complicated expression comes up. So I thought of like codes are already embedded over here, so I thought of just I'll just create it over here in a markdown file. So as you know that when we are over here, you have multiple options come up. So when you need it, you can create PDF also, you can create in Word file also. So let me just open up the PDF also. So this is the PDF file. So this is the PDF file, which you can see that this is the usual view, which looks like, right? So multivariate normal distribution plays a very wonderful role. The first few like around half an hour, I'd like to talk little bit about the math part of it. So then we'll get into the. But here also all the codes are everything embedded inside itself. So this is basically what is the probability density function for a multivariate normal density. So where mu is basically, we call it as a mean function, or the mean of that mean vector, and sigma is basically the variation or variance covariance matrix, right? This is what we call it. So just to have a match with this, with the univariate probability density function, if we just put p is equal to 1, and then this quantity actually converted to this form. So, and we know that this stands for the univariate normal distribution. So just to ensure that those are from stat background, a bit of exercise for them, that if x follows with normal mu sigma, we say that then expected value of x equal to mu and covariance of x is equal to sigma. And if we can transform this, that y is equal to, that is the sigma inverse and x minus mu, then we get the, right? Then we get the standardization of that multivariate normal we do in that case, right? So this transformation is very equivalent or is similar to what is the shifting and scaling for a normal variate when you do. If x follows normal mu sigma square, then we say that x minus mu by sigma, this follows normal 0 comma 1. So in this case, when we perform this operation, the new random vectors y, it follows a multivariate normal, but its dispersion matrix is identity matrix, and also its mean vector is 0. So these are the usual thing. Now let us try to visualize that how this bivariate normal density actually looks like. So these codes will be with you. This document will be shared with you. So when we say that, so bivariate means there will be two components. So basically we are going to look at this probability density function over the plane, right? So it is going to look like a surface for us. And this is mu, we say that's the mean vector, and sigma we say this is the variance and covariance matrix, right? So let us first write down that, since it is an R workshop, this is the one. Let us write it down for 2 by 2 scenario. That means sigma is a 2 by 2 matrix. So we have to compute a matrix inverse of this, and we have to compute this complete quantity and take an exponential of it, and we need also determinant of this variance covariance matrix below, right? So these few operations that we need to do. So let us try to see how we can do that. So suppose that mu is equal to 0 comma 0, which is going to be so few things I will write down also together, but these are some of the complicated expressions in these are appearing. So I would suggest you to, this code will be with you, so no problem at all. So this is going to be the mu vector. So means mu and mu t is 0 comma 0, and sigma is the variance covariance matrix. So it is 1 0 0 1 means it is 1, this is 0, this is 0, and this is 1. So it's this matrix is a diagonal matrix with variance covariance matrix 1 comma 1, right? So if you just want to get a feeling of this, that how this document looks like, as you see that this is the documents, how it looks like. So within this R environment, I have written this part. Say for example, this is the sigma. Let me just give you a feeling also, otherwise you will not get a feeling of hands-on, right? So you all know about par MF row. Par MF row, this basically divide a region, divide this window into two parts. So there will be two pictures, right, side by side. So if we just print our sigma, how does it look like? So you see that you have got a vector, or you have got a matrix, 2 by 2 matrix. And this is the function which I have written, that 1 by square root over, right, 2 pi square root over determinant of sigma. So this is the function determinant. If you want to calculate the determinant of a matrix, you can calculate like this. So it is a diagonal matrix or identity matrix. So determinant must be 1. Another part is that this is another new function probably you are looking at, solve of sigma. So it is basically stand for if you want to compute an inverse of a matrix, right? Because in PCA and all multivariate methods, this matrix is going to play the main important role. Say for example, if you, just for an understanding, if you want to calculate a matrix, say this is the way you can create matrix. Data is equal to say 1:4, right? That means 1 2 3 4. It is going to give you, say n row is equal to 2, n col is equal to, right? So if you print A, this is what you are doing it. Now you see that the matrix is being filled with first column 1 2, then 3 4, right? So this is what we call it as a, that first when you are assigning some numbers into a matrix, first it fills up the columns, then go for the right the column wise it fills. However, you can also mention an option over here, by row is equal to true. In that case, if you print your A, you see that now you have a row wise filling. So first it filled 1, 2 and 3, 4. You can compute determinant of A, it is -2, and you can also compute inverse of A, solve A. So this is basically the inverse of the matrix A, right? So let me calculate. Let me first print A, then let me calculate inv underscore A. Let me call this as an inverse of A is equal to solve of A. So let me print inv underscore A. Right? Now we can actually verify whether this we have got as a really the inverse we have got or not. So how can we verify it? If we multiply A with this inverse, we should get an identity matrix. So let's multiply it. So A star inv underscore A. Okay. We are not getting identity matrix. It's not an identity matrix, right? Yes, the audience?
Yes, sir. It is
It's
not
not an identity,
identity
right?
matrix.
So R has given something problematic. Any suggestion? Because if we want to calculate the inverse, then A into A inverse should be equal identity, right? But it's not giving that. Okay. So the idea is that what you are looking at, this is, say for example, if you give two numbers, 2 is to 3, 2 into 3, you get a 6. Right? If you give 2 into, so 1 is to 4, then all these numbers, so 2 will be multiplied with 1, 2, 3, 4. Right? So these are actually usual multiplication. This star is not a matrix multiplication. Okay. So what will be the matrix multiplication? Is A, this symbol, inv underscore A. Now you see that we got identity matrix, right? In the diagonal we have 1, 1, in the off diagonal 0, and this is actually 0 only because 10 to the power minus 16. So it is actually 0 only. Is that clear? Because this is a very common mistake, or at least it took some elongated time for when we are writing big programs, because we just put it a star as a multiplication, but matrix multiplication is, this is the symbol for matrix multiplication. Okay. So the density function what we had, this is the function what we have over here, right? So this is just as a whatever the math expression you have seen, I have just written it over here, and it is a function of x, sigma is fixed, mu is fixed, and it is a function of x. Now let us try to plot it in a xy on the plane. So for that, we discretize first that x1. You see that a sequence of x1. So it discretize. If you print your x1, so the way you discretize an interval, right? Similarly, discretize x2 also, right? Then at each of the values of pairs of x1, x2, we are going to create the value or the compute the value of this function f-val, right? So how many f-val is going to be a matrix, right? Its dimension would be number of row would be length of x1 and number of column would be length of x2. So it's going to be, values are going to be stored in a matrix. So let me calculate this one, and then let us compute this functional value. So at each pairs of xi and xj, we are computing the value of the function fx, right? So let us compute this. Yes. So let us see how to view what are the computation being done for a val. So if you use the view function, you can actually get an Excel like thing over there, right? Yes. So here it is 27. Top also it is 27. The discretization which I have done over here, it is the length is 27, right? So we basically calculated these different values. Now the idea is that you have x1 axis, you have x2 axis, and you are going to have a this type of shape, a bivariate normal distribution, a kind of surface you should get. So first is the function which perform that wonderful task for you. So let me just do that. I'm not sure whether this function being introduced or not. So this is actually, you can see that this is the one uh, which is the probability density function which you are getting over here, right? So you get a surface over here. So I can just plot this function only 1 comma 1. You see that this is the probability density function what we have got. So it's a bivariate probability density function. So area under this curve or volume under this surface is going to be 1, right? So you can actually, there are different option, this theta, phi, you can later play with these options actually. Say for example, if I just make this theta is equal to say minus 70, to see that the shape is going to change, right? If phi is, say for example, if I give 60, you see that this is what kind of orientation you want, that you can actually play with it. So there is a wonderful package what is called as a RGDAL, by which, so I'm not going to talk about this over here, where you can actually dynamically play with this graph, that what is the best possible look you are having, and accordingly you can you can save that particular view. So this is a wonderful comment. So I'm just putting it as a comment here so that later you can when you are understanding it, so later you can get it. So you can use, right, RGDAL package to get different views of three-dimensional plots. If possible, I'll include some examples also. So as you see that why I actually wrote it over here is to give a feeling that this R comes up with a whole sorts of a wonderful like capability in document generation. So this is truly like ex, like exceptional thing it actually offers. Okay, so this is what we have done for this. Now one important thing over here I want to point here. So let me come back to this picture again. Let me draw this once again, and let me draw it. Paramifro C 1, 2. I need 2. This is the first plot what we have got. Here I have put rho is equal to 0. Rho is basically the correlation between x1 and x2. So you observe that this plot, one thing is there, I'm not sure whether you have come across this situation here or not, but you see that in this plot we are able to put mathematical expression also, right? So you did not have to write RHO is equal to rho. So the expression is the in the main you can add that expression comment, in between you can put the LaTeX, what you put is the take, that comment you can write over here, and you can get the mathematical expressions on the plot wherever you want, right? So this is the first plot which we have got. Now let us try to get the, if we change the row, that means now the random variables are correlated. In that case, the sigma, this is the sigma that I have set it over here. So if you put this sigma, it is 1, 0.7, 0.7 and 1. This is the matrix. So they are correlated, right? Because the diagonal entries are non-zero. I mean, off diagonal entries are non-zero. Again, you do the same thing. Then again you get a compute this full process. So this is we can see over here. Now you can see there that when they are highly correlated. So let me plot this separately. For mf rho is equal to c 1 comma 1. So let me just draw the last part. So one thing you observe that earlier picture, this is very important actually. This has because this is a very serious connection with the multicollinearity, because you had already a session on regression, I think. So as you see that here the density function, you see that this is there is no particular direction. So it is like along the x1, along the x2, like the spread is almost same in both the directions. So there are sufficient spread both along x1 direction, both along x2 direction. However, when we put x1, x2 are highly correlated, say 0.7, and you see that, can you see this is the, if you think, imagine this is this diagonal line, that if you can draw one diagonal line over there, you see that most of the spread actually happening along this line. Whereas if you take an orthogonal line of this, the spread is very less. This will be more clear to you. Suppose I put here 0.9, rho is equal to 0.9. Again, let me plot it. So I have to change it over here also. So 0.9 and 0.9. Let me plot it over here again. Are you observing that it is getting more shrinked along a line, right? So that means in such a scenario, it will say that x1, if we know x1 with a very like you have a very high correlation with x2, so you basically know x2 as well. So this is a typical scenario when you say it is a multicollinear situation. So which is a very common scenario in current research domain, because you usually end up with a whole lot of features or whole lot of predictors, and many of them are actually correlated. Then you apply a lot of regularizations and everything other techniques you do, by which you can drop all those what is called as all those variables which does not seem to be, which does not have a such collinearity situation. So as you understand this picture tells you, this bivariate distribution tells you that if we try to understand that variation in x1 and x2, most of the variation is actually happening along this line, because here the spread is very high. Whereas if we take an orthogonal line over this, then the spread is very small. So any question here, this part is very important, because if you understand this, then principal component analysis will be very easy to understand. Is it understandable?
Sir, could you please explain orthogonality condition related?
Yes, I'm again explaining. Yes, again explaining. So what I'll do, just let me just do over here. I get, say I'm plotting 4 pictures. See 2 comma. I'm plotting 4 pictures. Okay. So how can we do that? Say I'm just considering. So this is a good learning for you as well. That it provides you so much flexibility that in a very short span you can do a lot of things. So let me just create 4 sigmas. Okay. Or maybe I can just consider a row vector. So rho is equal to c, say 0, 0.3 and 0.7 and 0.9. Okay. So that means 4 different graphs we are going to get, right? So then what I'm going to do over here, next task I'm going to do is that I'm going to get 4 plots. So this is the 4 plots I'm going to get. Then I'm writing that for R in row. For loop we are writing. So that means this R will, or more nice you want, then row in row underscore val. So that means I'm going to get 4 pictures with different rows. Okay. different row values. That's the correlation value. So then inside this loop, I'm putting this whole thing, that my sigma matrix is going to be this one. This inside this loop, I could put one. Okay, so here I am just changing this matrix with row and row, right? So I'm just putting this. I'm just putting expression part later. So just paste row is equal to say row. Let us just see what it is coming. So these are different row values. Let me just execute this part. 1, 2, 3, 4. Yes. Now you observe that for you row, can you see it is a kind of a circular shape? Yes or no? In the base?
Yes, sir. Yes.
Yes. As your row increases, can you see that it is becoming an ellipsoid shape on the base? And here ellipsis major axis is getting elongated, whereas minor axis is getting shrinked. And here the major axis is got heavily elongated, whereas minor axis got heavily shrink. So that means x1 and x2, they are very highly correlated. So this is a typical scenario, what we call as a multi-collinearity situation. Is it clear now?
Sir, does
Yes,
this
sir.
signifies the presence of linear regression between the two factors under consideration?
Absolutely.
Okay.
Because that precisely the connection between that if we write down the conditional distribution of x given x2, that is the mean part is nothing but the regression equation, right?
Thank you.
Yes. Thanks for pointing this out. But this you observe that many things when we are also doing our MSc statistics, many things as an equation professors used to write, but we at our time we are not able to visualize them so easily. Now R is now with this invention of lot of wonderful softwares and packages, and basically simple programming platform they provide. With that we can actually visualize many concepts. As you see that now we can have a wonderful possibility of regression over there, right? So I hope this part is clear. So just for a part of your documentation, I'm just putting it in a separate. So let us now plot some more figures with different values of row. As you see that we can write down LaTeX comment also inside, so it automatically and everything automatically your document will be updated. So what the document I have prepared for you to show, after I write all these things, the document will be automatically updated, right? So this is, I think we already have this picture. Okay. Now this is another scenario, right? This is another scenario. So in the case we have seen that we have the variation is basically equal. So both the diagonal entries are same. The sigma was 1 1. So we can have a different scenario. Also we can have the diagonal entries are different also. So in that case, how the situation look like, you can have a look at it. Say for example, here we have a, so let me take only one picture, C1, 1. So as you see that here these guys are not dependent on each other, but along this x2 we have a much higher variation, but along this parallel of x2 much higher variation, whereas parallel of x1 lower variation. So that means the variance of x1 is less as compared to variance of x2. The same thing you can do when you can have another possibility. So here basically you see that along x2 we have much variation, like, sorry, along the x1 I have a very large variation, whereas along x2 I have a lower variation. So this is very, very important that we understand the associated geometry with geometrical shape. This helps us to understand things better. Okay, so by doing this, then let us now go back to the document once again, which will be shared with you. It will help you to understand things better. So some more code has been updated in the file. So these are the couple of pictures which I had just generated there. Right? Okay. So this is a very important result that sigma is a diagonal matrix, and with all sigma is they are equal. So then the constant probability density contours, which will be a spheroid in the p-dimensional Euclidean space with center at mu, and the corresponding radius is going to be square root over lambda times c. So this is basically what is called as a constant probability density contour, right? And if these are different, then in that case it is going to be a p-dimensional ellipsoid. So it is going to, in the Euclidean space, it will be an ellipsoid. So it will, some portion is going to be bigger, some portion is going to be, some dimension is going to be less. So depending on that variation. Okay. Now these are some of the results. So related to the and some properties of the multivariate normal probability distribution. So these are not, I'm not going to share for statistics people. These are going to be kind of repetition for them. This is where I want to spend little bit time over there, because when we are dealing with R and we are dealing with a multivariate normal probability distribution, it is important that how we can generate the multivariate normal or values from a multivariate normal probability distribution, right? This is very, very important. And R does provide, there are different ways of simulating random numbers or multivariate random numbers from using uh, from the desired probability density function. So, so here this is what is called as a Cholesky decomposition. I have put the codes over here, that if you don't want to use any inbuilt random number generator from R, still you can generate your random numbers the desired number from the desired distribution. You can generate it. So one of the using a Cholesky decomposition, and there are other methods as well. So here, what I have just done over here. So first of all, that the matrix that we have written sigma, it has to be positive definite matrix. So if you see that library cluster generation, first time I am using a library. So this library called as this is a very, very important library. Yes. So if you know now how to load the library, so you just have to write down the comment library. This one is done, and generate a matrix using this library, random matrix. If you print your M, this gives you, right? It gives you the eigenvalues. As you see, all the eigenvalues are positive, right? And the corresponding matrix is basically this one. So how can you extract? So when you print it, when you see these dollar symbols, it gives you an indication that from that object, how actually we can get the our desired result, right? These symbols are telling you. So if you want to know what is the class of M, it's a list. It contains two things. One is eigenvalues, one is sigma. If you want to know that how the structure of M looks like, so you have to write down str of M. So it is saying that it is a list of two. Eigenvalues is this, which is numeric type, and then we have a matrix which is also a numeric type, which contains sigma. Is it clear? So this is important, that when you are using any existing packages, it gives a kind of an object. It may have different kind of object. So by looking at the structure of that object, you can actually understand that what are the things we need. So I need the matrix from here if we want to generate. So right. So if you now print this sigma, so this is the sigma that we have got from here, right? There are does provide suits of methods actually. If we just write down eigen of sigma, so this gives you eigen decomposition, so which gives you the corresponding eigen values, and it gives you the corresponding eigen vectors also, right? So these are the corresponding eigen vectors. So what is basically Cholesky decomposition? There is a nice function called Chol. I have already mentioned here over here. This is the algorithm which uniquely give you a choice of t, which is right. And this is the algorithm. One can easily write it down when you teach it in MSc program over here. Then we don't allow them to use the Chol function directly. They have to write down this function explicitly in using R, so that they get more comfortable with the environment, programming environment also. So let us take this, perform this decomposition. So we got this T, right? And what is sigma? This is the sigma. So T transpose T should be equal to sigma, right? So we can now verify that this T stands for transpose, and we have a matrix multiplication, right? And T. So if we dig it, as we observe that these are the same match with sigma, right? So that means it has given us the right matrix what we are looking for. So when you are creating a document, you can actually print this all the things. It will give you comment also. Check whether the decomposition works or not. And another important comment actually you will be learning over here, all dot equal. So if you give two matrices, it is going to check whether A and B, these two matrices are same or not. Element wise comparison of matrices, right? Say for example, if you, so I think this is over perfect over here. So if you just run this part, so it says true. That means what? That means what T transpose T give you and what sigma give you, this basically are same. So most of you, because some of the people are from research scholars, some of the people are teachers, so this is a common tendency. So this is a common tendency for many places what I have seen, even when you go for teaching in refresher courses and other places, we observe that there is something ready-made code, something is available, and we try to take that same thing and try to, that this is how it is work. R works in this package works that. So it is very important when we are as a research scholar, so when as a student, it is very important that we utilize that platform as a programming platform. So you understand lot of stuffs over there, get comfortable with loops, and implement lot of functions, which will give you a very comfort level with the software you are using, and automatically you are going to get the information about the various different packages. So it is byproduct, you will automatically get it. Okay, then another possibility is that if you want to get a, this is called a spectral decomposition. This is another multivariate analysis, multivariate methods. Any book this is going to contain it. So you can decompose sigma also like this, and you can then further decompose D to be d to the power half, you call it as a, and since all the eigenvalues are positive, you can create this one, right? A d half into d half is equal to d, since only the diagonals are there, so you are going to get a diagonal which is square root over lambda. So you get this you finally get this sigma half and sigma half. Sometimes people also call it as a square root matrix, right? And sigma half. This is interesting that the new matrix, the two new matrix we have got, it has also eigenvalue and eigenvector pair as square root of a lambda into ei. The main important part is that the same eigenvector what you had with sigma has the eigenvector eigenvalue pairs lambda I square root over ei. The same eigenvector should be retained over here for sigma square to the power half. This matrix also, only the eigenvalue is going to be square root over that. So this is also very important information, right? So again, I have put this code over here, so you can easily get that, and you can perform this analysis, and you can find out what is the matrix of P. So you create the square root over matrix and do the whole process, and create the square root of sigma, and then again you check whether you get all equal or not, right? Right? So why this is actually important, now it will be clear to you. You all have learnt about one interesting theorem. I think you call it as a probability integral transform. So can anybody tell me that whether you have learnt it or not? Anybody say yes or no? Anybody? Yes. What we called as a probability integral transform. Anybody
Yes,
knows?
sir.
Yes. So what actually it says?
Sir, it is actually just X is a X has distribution fx. Then
Yes.
what if we take another random variable y? We can take transformation. We can get fx equal to y. Then we get the distribution of y in terms of
Yes.
x. Actually.
Yes, you are absolutely correct. What we say that the probability integral transform says that you can simulate any random number, any desired random number by from the uniform probability distribution. So the idea says that if you have a distribution, where did you go? It says that if your x follows a random variable capital F is its distribution, then capital F within bracket x. So that means it's a new transformation. This is always going to follow uniform distribution. So that means if you can simulate random variables from uniform distribution and take the inverse mapping of F inverse of the uniform distribution, you are going to get the desired probability distribution. So what is it actually telling us? So for many people probably it is not clear. Let me just tell you, just immediately I can show it to you. Say for example, what is the function if I write a function x, sorry, exp of minus x into x bigger than 0. So if you draw this function curve fx, say -1 to 3, and you take call is equal to say rate, right? So let me take it as a single page. Why actually I'm doing this hands-on? Just to give a understanding that it is super simple. So if you just want to utilize R, you can just play with it like anything, right? This is the function. This is I have plotted it, and I can put some line with. Statisticians can identify this density function, right? This is what is called as a exponential probability density function, right? Yes or no? It is a exponential density function.
Yes,
I
sir,
can
yes.
plot it over here, right? This is the plot, and whether it is a density function or not, we can immediately check it by integrating f from 0 to infinity. The integral is 1. So it says that it is a valid probability density function. Now suppose that I know simulation of random numbers from the uniform distribution. What does that mean? Say I know y is equal to r unif is the function which performs that. Say 100 numbers I generated. Mean is equal to 0 and max is equal to 1. Right? If we draw a histogram of y, probability is equal to true. So this tells me that it's like more numbers I generate. Say I generate 500. So it is going to approximate the uniform probability distribution. So you can add a curve to it. D unif x call is equal to rate, line width is equal to 2, and you can add that curve to it, right? So this is basically says that as you see that more data point we take, the corresponding histogram is going to approximate the actual uniform probability density function, right? So what probability integral transform says that what is the CDF of this exponential density function? The CDF of is so capital if I write down, a function x, so it is going to be 1 minus exp of minus x, right? If somebody statistician is there, they can correct me. So if I draw a curve of it, curve f x call is equal to rate and line width is equal to 2, and maybe I want it from -1 to 6. So this is actually the CDF of exponential probability density function, right? Now you observe that suppose that yes or no. Now what is going to be inverse of f? Then how do you do that? We write down y is equal to 1 minus exp of minus x, right? Then 1 we are going to take it this side, so y minus 1, right? Then this minus minus will get cancelled, so we can write down 1 minus y. Then we can take both the side log, so I'm going to get exponential will get cancelled, so we are going to minus x, so we can take x over here, so this one. This is nothing but inverse of the function f. Right? It is inverse of the function f. Let me write down inv underscore f is equal to another function x. What will it be? Minus log of 1 minus x. Right? This is what we have got over here. So how many things we have got? We have got the density function from which we want to simulate, right? So maybe we can just take 4 pictures at single time. C 2,2. So this is our first picture. I think I will just drop this part. This is the first picture, exponential density from which I want to simulate random numbers. This is the uniform random numbers I have generated. This is a guarantee for that. So I got 500 uniform random numbers. Then I computed the CDF of this function, right, which is 1 minus x. Then I have computed inverse of this CDF, which is minus log of this. Now I pass this random numbers what I have got from uniform 0, 1 to this CDF. So that means I am writing that x is equal to inv underscore f. These numbers y, that uniform random numbers that we have simulated, passed it over here. Now let us draw the histogram of x. Probability is equal to true. And say call is equal to some light gray, probably you can write down. How this histogram looks like? Is it a match with curve of fx? Yes, it is true. You can add a curve fx. Call is equal to red and line width is equal to 2, and you can add this curve to it. So yes, these are the random numbers what you have got. This is from the uniform, your desired random number. So this is a very fundamental theorem in statistics and probability, that you can just simulate any random numbers from any probability distribution if you know how to simulate from the uniform 0 1. How to simulate uniform 0 1. How this is relevant to ours, what we have tried to show it over here is that if you know how to simulate from standard normal random variable, from that you can go to any desired any desired multivariate normal distribution of your interest. Making sense? So what we did it, so if we just take, we know what is mu, we have to simulate from x, we know what is t, right? And z, if we perform this operation, we know that z becomes its mean vector becomes 0 and its covariance matrix become identity matrix IP. So in both the cases, if you use this transformation, z becomes normal distribution. They are basically uncorrelated normal. So the above results can be utilized to simulation random numbers from the multivariate normal distribution for some given mean vector and variance covariance matrix. So Z1, Z2, Zp, you simulate from IID normal 0, 1, and then this is the algorithm you follow. Take the input mu and sigma, you simulate Z1, Z2, Zp, and write down in the matrix form, and you compute sigma transpose in this fashion. Compute sigma transpose sigma half with the algorithm we have just said, and then you perform this one, and the value, the vector that you will be getting, it is going to be realization from this. So here an example is also given. This is the example which you can see over here. So this is the input I have given, mu vector. This is the matrix, which is the sigma matrix we have given. So this is the sigma matrix. I want to generate 500 random numbers from normal, and each of them will have a triplet, right? So each of the observations will have a triplet, and I need a 500. So 5,000 such values. So we calculate the p eigenvectors, and we calculate the corresponding lambda values, and we calculate the square root over the sigma matrix, right? Then I just simulated these values where things are going to be stored. So I allocate the array. So no values there till now. Here I am going to put those values. I am going to generate from normal random variables only, nothing from anything else, only from normal 0, 1. Then whatever z being created, they got this transformation, x is equal to this, and I just filled up the ith row of the simulated values. So by now you got, because a lot of our sessions you have seen, I'm assuming that you got comfortable in it, but anyway, the code will be there with you. These are the values. This part is very important for real life application, that whenever you get some data, you need to check that whether the simulated data, whether the obtained data follows a multivariate normal or not. So here we can say that library MB norm test, from here we have the multivariate version of the Shapiro-Wilkes test that can be performed. So those who, if is not covered over here, remember that this is one of the most useful function in real data analysis, that if I say simulate some number R norm, n is equal to say 100,000 numbers I simulated, mean is equal to 2 and is equal to say 1, then Shapiro.test x, this tells us whether the data has follows the multi-normal distribution or not. Okay, and its multivariate extension is, it is the M Shapiro, what I have shown over here, which is a part of the library MB norm test. So in this library you have this availability of this. Okay, so then you can draw the histogram of each of them. each of the component. So each of the component must be normal probability in univariate normal distribution. So if I have a jointly distributed random variables which follows multivariate normal, then we know that the corresponding each of the component, the marginals distribution also turns out to be normal only. So as you observe that here means are 20, 55, and I think it is 4. So what was our mean vector? Let us check. Twenty, 55, 4. Yes, it has done the right thing. So please at your home, because it's a very less time, or rather than it is very online mode, I'm not able to check that. Right, but session is recording. That is a nice thing. So this is basically what is another very important plot called as a pairs plot in R. So it gives you the values we have generated. So x1, x2 are basically uncorrelated, right? Whereas x1 and x3, they have slightly negative correlation. Whereas x2 and x3, they have slightly positive correlation. That is how we actually read the pairs plot. Any doubt till now?
So, is FPO will detect any kind of non-parametric test or parametric test?
Sorry, say please, can you repeat?
That normality test is in non-parametric kind of test, yeah, or it is a parametric test for testing the multivariate normality of the data?
I think this is parametric test only, because I'm just immediately not able to recollect the test statistics, but it is a ratio of two things comes up. The sum of squares and two ratios are comes up. I guess it is parametric only. Okay. Thanks for the question. But if I said it wrong and if you know it correct, please don't hesitate to share. Okay. Yes. Thank you. Okay, the same thing I have told over here, that it is a, what we call it as a, that the same process you can also do using the Kolesky decomposition also, which is given over here. Again, you can take it from here. Then we have but now this is the most commonly people use, that you can create this, what is called as a this MBT norm. This is the package. There you can actually directly calculate what we call as the random samples from multivariate normal distribution. So this you can easily do that. So this code will be there with you. Now this part is very important. Again, a bit connection with the principal component analysis. So what it says that there is one important concept called as a generalized population variance. So what is that actually? So all of you know that if I have a what is called as a determinant of a matrix is actually the product of the eigenvalues. Yes or no?
Yes, sir.
Yes. So if one of the eigenvalue is very small, say close to 0, in that case determinant also must be very close to 0, right? So
Obviously.
yes. So what is its real impact actually? What is happening if such a scenario comes? I just try to put two things over here. One is that I get a sigma 1 where the eigenvalue is 3 and 2, much much away from 0. So determinant of sigma 1 would be 6. I got another sigma 2, that where one eigenvalue is 3, another one is 0 0.3, 0.1. So its eigenvector, its determinant is basically 0.3, right? So then I created these two pictures. As you observe that here I have variations along x1 and x2, significant variation, but whereas here if you take care of the variation across x1, very less variation is remaining along x2, yes or no? Yes, if you see that this is the variation here, there is a very high variation over here, sorry, along x2 basically, sorry. Along x2 I have a very high variation, but whereas along x1, perpendicular direction, very less variation is remaining, right? This is again the scenario. So this part is very important. Earlier I have talked about you with multicollinearity, but here we are making sense of multicollinearity in terms of the eigenvalue of the variance covariance matrix. If your some eigenvalues are very small, that also is an indicator that your variables are correlated. So what is the conclusion? So mod sigma is called as generalized variance. It has certain nice geometric visualization, but I'm not covering it right now. If it close to 0 means that one or more eigenvalues are close to 0. This means that the variables are highly correlated, that one of the variables can be represented as a linear combination of others. This is very important concept, and we know that it is called as a multicollinearity in regression modeling. So let me just summarize it. What is a multivariate normal distribution? Each of its component follows univariate normal, and if we visualize it on a plane, this is the density function it looks like, right? And we can have spread along one direction, and this is the direction of the highest spread. So this is the direction, if we consider, is the direction of highest spread, and these highest spread directions are actually called as a what is called as a principal component. So let me just take you to there. Now I think we are done with that. It is just a little bit of math part we're doing. We'll take the small break, then getting into that context. So again, here is that if we have a random vector with covariance matrix sigma with these eigenvalues, then we write down the linear combinations, p many linear combinations of the original random vector, which are this. You can easily verify this part. So what principal component is? The principal components are those uncorrelated linear combinations y1, y2, yp, whose variances are as large as possible. So those who are from a non-statistics background, a slight visualization will help you over here. So if you observe this data, right? Along x-axis I have population, along y-axis I have ad spending, and we made a scatter plot of it, right? So I have a variance associated with population, we have a variance associated with the ad spending also, right? Now if you observe this particular line, if you observe along this, if you see that the most variability in the data is happening along this line. And how we can get this line? This line is nothing. It is a combination of this x-axis and y-axis. So we call it as a linear combination since it is a line. Like if I rotate this axis along this direction, so let me just write it down over here. So let me get a pointer options and pen. So what I'm saying that this is your axis now, and this is your axis now. If you rotate this axis and get this as an axis and this as its perpendicular axis, now this is the variation, large variation along the axis you are going to have, right? However, if you look at its perpendicular direction, means this is 90 degree, there the variation is very less. So the direction along which the data has the highest spread is basically causes the first principal component. Then you take its an orthogonal direction, means you consider one more axis which is perpendicular, and the second and the variation which is the smaller than this variation but bigger than all other axes. Then we call it as a second principal component. Then again, suppose that you got two principal component like this. Now you get it, it's another perpendicular to this. So maybe I can just draw a picture over here. Suppose that this is two perpendicular line, two principal components. Then you look for another component, which is the third principal component. So which is called as the third principal component. So as you understand that, we are trying to understand the variation in the data by changing the actual axis and creating some new axis. I hope I am able to make sense for the non-statistician people. So this is something what is called as a, so the principal components are those uncorrelated. Why it is uncorrelated? Because this component, this direction, if you say it y1, and this direction you say it's y2, y1 or y2, these are basically perpendicular to each other. They are orthogonal to each other. So that's meaning is that they are uncorrelated, right? And they are again a linear combination, because these are linear combination of the original, right? Now the question is how to determine that. If you determine that, you have the original vector matrix, original say sigma matrix, covariance matrix, and immediately you can compute the eigenvalue and eigenvectors. So that we have already learned over here. If we have a sigma matrix, if we write down that eigen of sigma, then immediately we get the eigenvalues and eigenvectors, right? These are the eigenvectors that you have got over here, right? So you got the eigenvalues and eigenvector pairs that you have got, right? So yi is equal to ei transpose x. That means this one, I is equal to 1 to p, right? So that you have got the choice of now the linear combinations, that a11, a12, this one that you have got, right? So this becomes the yi's. So this one is become the first principal or the ith principal component. And what is the interesting property? Variance of yi is actually lambda I. But what is lambda 1 lambda 2 relationship? That lambda 1 is the maximum, then lambda 2, then lambda 3, then lambda p. So that means variation of yi has the maximum variation. So variation of y1 has the maximum variation, which is lambda 1. So this direction is basically the E1, that eigenvector corresponding to the eigenvalue, which is lambda 1, which is the maximum eigenvalue. Is it clear? So geometrically making sense? Okay. So just with this comment, Dr. Joshi, please tell me when to give a break for the participant. Okay.
Sir, I think we can have a break now and can reassemble in 10 minutes around 11:30.
Okay. That is also fine. That's okay. That's okay.
So, like, is there anything which is to be covered for this particular?